arithmetic, multiplication is not commutative, right? Okay, Rebecca.
So if you do an entire omega and then an entire omega and then another omega, is it omega times 3?
Yes, it's omega 3. This is omega 2 plus 3 because I put 3 points there. Okay? Yeah, so you can keep going. Go crazy. Here we go. Plus 1, plus 2, dot, dot, dot. And then the next one, if you could go beyond that, take the soup and you get omega 3. And then, okay, omega 3 times plus 1, omega 3 plus 2, dot, dot, dot. And then you get what? Omega 4. Oh, and then after a while, you get omega omega, which we call omega squared. Yes? That's okay. And then omega squared plus 1, omega plus 2, blah, blah, blah. Past some point, you get omega squared plus omega. That's all right, yes? Etc. Dot, dot, dot. Eventually, you get omega cubed, omega to the 4th, dot, dot, dot. Eventually, and take the successor of all those, you get omega to the omega. These are all countable. These are still all countable, okay? Then, keep going, omega to the omega plus 1, omega to the omega plus omega, omega blah, 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 dot, 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 okay. Eventually, you get omega to the omega to the omega. And then you get omega to the omega to the omega to the omega. Still countable. Large but countable ordinal, okay? And eventually, past all those points, you get to something we call epsilon naught.
Wait, when did the permittivity of free space get here?
Yes. Yes. And omega naught is defined to be the first ordinal. What? Epsilons of naught, yes. Is defined to be the first ordinal that satisfies the property. The ordinal epsilon naught is omega to the epsilon naught. So this is really, if you like, it's omega to the omega infinitely many times. Okay, countably infinitely many times. Okay, but there are many such ordinals that satisfy this property. So after a while, you get to omega, you get epsilon 1, which is also satisfies this property, but it's not the first, but the second one that satisfies this property, right? Okay, etc. Dot dot dot. These are all still countable. Countable ordinals. Yeah. Okay, so eventually then, you get to, past all these, you eventually get to the first uncountable ordinal, which we call omega 1. Okay. Then you can do omega 1 plus 1, etc., etc., etc. And keep going. Okay, don't be fooled. Don't be fooled. This is not the same thing as, we haven't just, by listing all these ordinals in a sequence, somehow proved that uncountable ordinals are countable. We haven't done that, right? Because when we said you can list things in a sequence, we really mean you can put it in an order type that's isomorphic to the natural numbers. But here we have some, lots of limited ordinals in between. Jenny. Interesting question. Very interesting question. Well, so all we said here was we just defined an ordinal to be the set of satisfying these properties. So, the first uncountable ordinal is basically, just like every other thing in this list, the supremum of all the things that preceded it. You can't stop me from taking the supremum of all the things that preceded it. And you can verify that, just by verifying property 3, that if you take the supremum of a set of ordinals, you'll get something that is an ordinal. Well, there has to be a first uncountable ordinal. Well, if you look at all countable ordinals and take their supremum, that has to be an uncountable ordinal, because it's not going to be every member. Every member is a subset, and it would be very silly if you took the set of if you took all uncountable ordinals and you took their supremum, and somehow that was a subset of one of the things that was already in the list, because there's other things in the list. Willie?
I'm wondering if there's not some greatest element below omega 1, is there?
No. Omega 1's a limit ordinal. Yeah. Yes. Okay. Now, of course, if you ask me too many questions, you're going to reach the limit of my understanding of set theory. But yes, Lindsay.
I was just gonna ask, you're writing these down in a certain order. Like, obviously, you're not writing everything down, but like.
Thank you.
But like, you're putting like a defined, like you're enumerating them basically. And can't you not enumerate uncountable things?
Yes, but when we say we can't enumerate, what we really mean is we can't place into a bijection with the natural numbers.
But like in between every one of these, like omega and 2 times omega or whatever,
Yeah.
can't you put that in a bijection with the natural numbers?
Yeah.
Couldn't you put each one of these dots that you have there in a bijection with the natural numbers?
Yeah.
So then how do you eventually get to uncountable?
Well, yeah. So I mean, the thing that's not clear from this is that there are. It's not clear to me either. Apparently, is that there? I mean, I think I hear what you're saying. You're worried that you can do some kind of enumeration where you take, okay, if I wanted to enumerate this, I'd take the first thing from every thing, second, and or do some kind of snake-like argument like we did for the rash. Yeah, you can't do that because there are I mean, okay, so look what happened. You want to do what you did. You would do that with, okay, the first omega, the second omega. So you go omega, omega 2, omega 3, and by the time you get to omega squared, you have that array that you could snake through. But there's way more stuff, right? And these all accumulate on each other in very funny ways. And so you won't be able to actually write out an enumeration if you tried of the things that are of any ordinal that's less than omega 1. Of omega 1, the things that are in omega 1. There's just too much here that's accumulating upon. I mean, you have a bunch of, this thing is a limit ordinal, but it's not only the limit ordinal of the things preceded, it's also limit ordinal, it's like a limiting ordinal of a bunch of limit ordinals. So it's really, what's happening here is really weird, okay? It's hard to convince you of that, but okay. So, so here's another thing you can actually say, and it's a version of the library paradox. You can't talk about the set of all ordinals, because if you could take their supremum, and that would have to be an ordinal, and then it would be somewhere already in the set, and then that, yeah. So you'd run into problems. So, the Russell's paradox. Define. Look at the catalog that contains the. Look at the catalog that contains the library catalog that contains how's it go? Every book. Look at all the sets that contain themselves. Sorry, I was trying to say this in terms of library books and stuff. The catalog that contains every book. Yeah, look at the sets. Look at the set of all. Look at the set that contains every set that does not contain itself. Is that a set? Well, if no, then yes. If yes, then no, and you run into problems with